In this section, we're going to learn about what are called parametric equations, or parametric functions. So the basic idea of a parametric equation is that we have some input, generally going to be t, but later we'll see sometimes we could use theta or another variable instead. And both of our coordinates, that's x and y, are going to be influenced by that input parameter t. Okay, so kind of an example of how we might use this. As time moves on, we might be using that to model the x and y position of an object. Okay, so we could think about something moving in two-dimensional space according to a time parameter, t. So there's a few different ways we could write that. We could write x equals and then give it an equation, and y equals. Or you could write that as an ordered pair, so the equation for x followed by the equation for y. And then also, there's a special name for the set of all the points formed in a parametric graph, and that is a plane curve. Okay, so to help us make sense of this, I want to look at kind of a practical example and make sure we can understand what's going on here. So in this example, we have a baseball being hit into the air. We have a function for its x-coordinate at a given time, and a function for its y-coordinate at any given time, and t is the number of seconds after we hit the ball. So the first question is find the position of the ball right when the ball is hit. So let's plug in t equals 0. Okay, I could write x of 0. In other words, I'm going to take this x function and plug in 0 for t. Alright, and then to find the y position at time equals 0, I'm going to plug in 0 here. That comes out to 0. So at the instant the ball is hit, it's at a position of 0, 0. Okay, so maybe this is cricket instead of baseball or something because it's right on the ground. Alright, then I'm supposed to find its position 1 second after the ball is hit. So let's plug in 1 into each of these guys. So negative 16 plus 64, that's 48. So 1 second after the ball is hit, it's at a position of 24, 48. The next thing it asks us to do is to graph the trajectory of the ball from t equals 0 to t equals 4. So to see what this looks like, let's make a little table of values. And what's going to make this different from maybe other functions you've graphed before is that I have 3 parameters to deal with, t, x, and y. So I'm just going to plug in the numbers from 0 through 4. Okay, there's nothing saying I had to plug in all of these or that I couldn't plug in other numbers like 0.5 and 1.2. I just picked some so I can kind of connect the dots. So we've already seen when we plug in 0, we get 0, 0. When we plug in 1, we get 24, 48. Let's see what happens when we plug in 2. If I plug in 2 there for t, I would get 48. And if I plug in 2 there for t, I would get negative 64 plus 128, so that's 64. If I plug in 3 for t, that would be 72. And if I plug in 3 for t in the y equation, let's see, that's going to come out to 48 again. And then finally, if I plug in 4 for t, it's 96, and then 0 if I plug in there. So let's go ahead and try to sketch this. I'm going to connect my dots, and we're going to see something new that maybe you haven't dealt with before. Okay, so these guys are evenly spaced. These guys are evenly spaced. So we start here at 0, 0. We're going to go to 24, 48, followed by 48, 64, 72, 48, 96, 0. So if I'm following the path of this ball, it arcs up, it reaches a peak, and then it comes on down. Now, something we may not have ever done before when graphing functions. With a parametric function, you can't just graph the points. Sure, that's the plane curve, but if I'm graphing a parametric function, I have to show the direction that this graph is moving. Right? It's not just all there at once. Instead, when we start, we're on the left. When we end, we're on the right. So I need to add at least one arrow showing that this graph is moving from left to right so I can see what's actually going on here. So that's the path that the ball is tracing here. Now, I've put this in the lecture notes if you want to click on the link and play with this yourself, but let's look at an interactive example of what's going on here. Okay, so we're going to start with the ball right here at time equals 0, and as the time value moves up, we're going to see what happens to the ball and where it goes. Okay, so I'm just going to hit play here. You can see the ball goes up, it reaches its peak, and then it comes on down. Okay, and if we loop it again, it's going to do that same thing. Now, I want to show this as a comparison to another example. We're going to graph another parametric function, and it looks a little different, but it's the same idea. X is 6t, y is negative t squared plus 16t. And I'm supposed to graph that from t equals 0 to t equals 16. So once again, I'm just going to make a little table of values. I do not have to plug in every single number, just enough that I can kind of connect my dots. Okay, so I'll just pick some numbers along the way and plug them in. Okay, so I encourage you, go ahead and fill in this table yourself. pause the video, then unpause and see if we got the same numbers. So if we carefully plug in, okay, if I plug in 0 for the x function, 6 times 0 is 0. I'll plug in 0 to the y function, negative 0 squared plus 16 times 0. Okay, I keep doing it for these other guys. Just plugging in for the x function and for the y function. Something interesting is going to happen. I want you to notice that these points we come up with are identical to the points we had in the first one. So if I went to graph it, it would look exactly the same. I'm hitting the same spots and I'm still moving from left to right. So the question is, how is it that when I have two wildly different equations, right, 24t and negative 16t squared plus 64t, or this guy, how can two equations generate the same graph? Or in other words, how could two parametric equations have the same plane curve? Well, it comes down to the fact that these are tracing that path at different rates. So I'm going to go back to that interactive example from the notes. I'm going to turn on the second one now. So we have our red path, that's the original one, and our green path, that's the new one. We're going to see that they trace the same path, but they're going to do it in a different way. So watch what happens as I let the t-values increase. The red one goes really fast. The green one's doing the same path, but way slower. Okay, so it's entirely possible that multiple functions can have the same plane curve, that's the set of all points, but they might trace it at different rates, or it's even possible that they might trace it in different directions. I could have written a different function that starts on the right and then moves to the left. Okay, so there's a lot more going on in parametric functions or parametric equations than there are in just regular old y equals equations that don't have a third parameter.